Hello, my name is Aidan Coleman, and this is my presentation for Physics 2211, Lab 1.
Today's objective is to observe the motion of a basketball that's moving at constant velocity. We'll use Tracker to track this object's motion, and then use GlowScript to create a computer model. In the end, we'll compare the observations to the predicted computer model.
The purpose of this experiment is to show practical applications of Newton's second law. The idea is that since there will be no net force, ideally there will be no change in momentum of the object over time, leading to that object to have constant velocity. The object being observed in this video will be a basketball rolling at constant velocity. The diameter is 24 centimeters and the mass is 590 grams.
Now, we'll be using the Tracker application to track the motion of the basketball. We have the purple line set up as the axis along which the basketball will be moving, and we have the blue circle as the center of mass of the basketball. A blue circle will be recorded for each frame of the video, eventually creating the position versus time graph that is shown on the right
Of the ball. Now here's the video of the ball rolling whilst being tracked by the blue center of mass circles.
Some key takeaways we can make after using the Tracker application is that the position versus time graph has a constant slope. This means that the rate of displacement over time is constant, or that there's a constant velocity. Because of this, we can say that there's no net force being applied because of the momentum principle, saying that the net force equals a change in momentum over time. And since the velocity isn't changing, there's no change in momentum. Now, we can use the data recorded from the Tracker application to find the average velocity of the ball. Since the velocity is constant, we can take 2 points from the x data and divide it by the change in time. I'll be using the first and last points of the x data and time data. The change in x position is 1.192 meters minus 0.0063 meters, then divided by the change of 1.467 seconds, giving us an average velocity of 0.808 meters per second.
We take our average velocity of 0.808 meters per second and multiply it by the change in time of 0.067 seconds to give us a vector of 0.0541 in the x direction and then 0 in the y and z directions. Now, here's a video of the computer model in action. Up top, you can see it shows the ball's motion similarly to as it appeared in the video, rolling straight to the right in the positive x direction. Here, the position versus time graph mimics that of the one on the Tracker application, although it is much straighter than the one on Tracker application because the computer model does not have any inaccuracies. Finally, here's a graph of velocity over time. Obviously, it does not change as it maintains a completely flat slope.
Now, we will be comparing the results from the observed and predicted models. The blue line is the predicted results used with the GlowScript computer model. The red line is the observed results from the Tracker application. As you can see, the results are quite close, with the red line being slightly below the blue line. This could be for certain reasons, such as human error when it came to tracking the center of mass of the basketball, or it could be because of unaccounted resistive forces, such as friction or air resistance. Now we'll see what would happen if we were to flip the x-axis during this process of motion. To do this, we'll change the velocity vector to negative 0.808 meters per second, so it's moving in the negative x direction over time. Consequently, we'll also have to move the vector of average velocity times delta t down below to negative 0.0541 instead of the positive that it was before, to represent the ball moving in the negative x direction. Once we run our program with the modifications made to have it have a negative velocity, we get these results. You see the ball moves to the left, or in the negative x direction because of the changes we made. Now you see the position versus time graph has a constant negative slope as opposed to the positive slope it has before. This is because it's moving in the negative x direction over time, giving it a negative velocity. And now for the velocity versus time graph, it has a negative constant velocity. There's no change in velocity over time, but now if you look on the left, the velocity value is negative instead of the positive value it was before. Now for a final question, is it possible to know how many forces cancel each other out to give us a net force of 0 in this situation? We know that gravity and normal force cancel out in the y-axis, but we do not know about many smaller forces at play, such as friction, air resistance, and possibly even electromagnetic forces. Because of this reason, we can't know for sure how many forces are at play.